we are going to learn about certain geometric shapes. Take a look at the following figures and identify some shapes that you see.
The first figure is the Star of David, which appears in the flag of Israel. It consists of two equilateral triangles that are linked to each other.
I also see outlines of triangles in the second picture, plus several squares.
Very good! Triangles and squares belong to a class of plane figures called polygons.
Miss Christelle, are circles polygons too?
We'll answer that once we get to know polygons better. We have the following definition.
Oh, so that means a circle is not a polygon after all.
Why do you say that?
Well, a circle has no corners or angles.
Besides, a circle has no identifiable sides.
That shows you understand our definition. The term polygon is derived from two Greek words, poly meaning many and gonia which means angle. Thus literally, a polygon is a figure with many, at least three angles. The point of intersection of any two consecutive sides of a polygon is called a vertex.
Are trapezoids and parallelograms polygons too?
Well, what do you think?
Judging from the definition, they are.
Yes, you're right. However, today we are going to focus on regular polygons, which are polygons where the sides are all of equal length and the angles are all congruent. Can you name some examples of regular polygons?
I think equilateral triangles are regular polygons, since they are also equiangular.
Very good, Maurice.
A square would also be regular since each angle is a right angle and all four sides have the same length.
Would a rhombus be regular, Miss Christelle?
Well, class, what do you think? Does a rhombus satisfy our definition of a regular polygon?
The sides are congruent, alright, but we are not sure if all four angles have the same measure. I don't think a rhombus in general would be regular.
Yes, that's right. The first 8 polygons in terms of the number of sides or angles are shown on the screen.
Miss Christelle, how did these polygons get their names?
Good question. Since the Greeks were among those who first worked with geometry and other fields of mathematics, a lot of mathematical terms we know came from them. As I have mentioned, gonia means angle, while the prefixes identify the number of sides or angles. Thus, a polygon with 6 sides and 6 angles is called a hexagon, and a polygon with 5 sides is a pentagon. In these pictures, you can see some regular polygons that exist in real life. Can you identify them?
The stop sign is an octagon.
That's the Pentagon headquarters in the second picture. I have seen it on news footages about 9/11.
The honeycomb cells are actually hexagons? Miss Crystal, do bees understand geometry?
They must have a reason for building their honeycombs in that shape. Perhaps you can research on this.
The last picture shows a nonagon. What is that picture?
That's the ceiling of a church in Uganda. So you see, class, we see these shapes around us. It is good to get to know them better.
Miss Christelle, what do you call a polygon with 99 sides?
It's for you to find out. That will be your special assignment for next meeting.
Me and my big mouth.
We will now identify certain properties of polygons. First, we define the diagonals of a polygon. The first thing we will investigate is the number of diagonals in a polygon. We will let n denote the number of sides, d the number of diagonals containing a given vertex, and big D the total number of diagonals in a given polygon. Let us begin with the triangle and the quadrilaterals.
A triangle has 3 sides and no diagonal.
For quadrilaterals, there are 4 sides and 2 diagonals.
How many diagonals are drawn at each vertex?
1.
Alright! To help us fill up the other entries in our table, let us use the following figures. I need volunteers to draw the diagonals.
Can I do the pentagon?
Sure, go ahead.
There are 2 diagonals that go through each vertex, and there are 5 diagonals in all.
Let me do the next one.
Go ahead.
The hexagon has 9 diagonals, and 3 diagonals pass through each vertex.
Very good. Now let's work on the remaining polygons together. Now that our table is complete, let's look for some pattern in the entries. Consider the first and second columns first. What do you notice?
The entries in the second column increase by 1, and each entry in the second column is 3 less than the corresponding entry in the first column.
Very good observation, Tisa. How should we express the relationship between n and d then?
How about n minus d equals 3?
That's right. So how can we get d from n using this equation?
I know. It's D is equal to N minus 3.
Yes, you're right. The number of diagonals that pass through a given vertex is 3 less than the number of vertices. Can anyone explain why this is so?
If a vertex is given, then a diagonal through it can be drawn by choosing a second vertex as the second endpoint of the diagonal. Thus, the number of diagonals that we can draw from a given vertex is equal to the number of points we can choose as the second vertex.
Good thinking, Doms.
Since the diagonal joins 2 non-adjacent vertices, we can choose the 2 vertices adjacent to the given vertex.
We also cannot choose the given vertex, since a diagonal cannot connect a vertex to itself.
That means that 3 vertices cannot be chosen as the second endpoint. So that's why only n minus 3 diagonals can be drawn.
You're all good, and I'm so glad you're learning fast. Okay, now let's turn our attention to the third column. Can you find any patterns in the entries here?
I see that the increase in the number of diagonals increase by 1 each time, since we have 2 equals 0 plus 2, 5 equals 2 plus 3, 9 equals 5 plus 4, 14 equals 9 plus 5, and so on.
You're very observant, Leia. But this means we have to know the number of diagonals in the preceding polygon before we can determine the number of diagonals in the next polygon.
Yes, I see what you mean.
We already know that there are n minus 3 diagonals that can be drawn from each vertex. Can't we just multiply this by the number of vertices?
That makes sense. Let's check if your suggested method works. In our table, the number of vertices is in the first column, while the number of diagonals through each vertex is in the next. Okay, let's see. In the first row, we have 3 times 0 is equal to 0, which is correct. In the second row, we have 4 times 1 is equal to 4. But our third column says 2. It seems our formula is not correct.
It's the same for the other rows. The product of the entries in the first 2 columns is always twice the corresponding entry in the third.
He's right. So instead of just multiplying the entries in the first 2 columns, we divide the product by 2 to get the correct number of diagonals.
But why do we have to do that? Joseph's suggestion made sense.
Let's try to see why this is so. We know that there are d is equal to n minus 3 diagonals through each vertex. So Joseph suggested that we just multiply this by the number of vertices. But multiplying is just adding the number of diagonals that pass through the different vertices of the polygon. Suppose we name 2 non-adjacent vertices as A and B. Then, there's a diagonal joining these 2. In the formula suggested by Joseph, we count n minus 3 diagonals at A and another n minus 3 diagonals at B. Can you tell what is wrong with this?
I think I know. We counted the diagonal joining A and B twice.
This happens for each pair of non-adjacent vertices, which means that we are counting each diagonal 2 times. So the product n times n minus 3 contains twice the actual number of diagonals.
And that's why we need to divide the product by 2 to get the correct number of diagonals in column 3.
Yes, class, you are right. So we now have our formula. Using this formula, how many diagonals would a dodecagon, which is a polygon with 12 sides, contain?
That would be 1/2 of 12 times 9. Or 54.
Yes, that's right. Imagine how hard it would be if we have no formula and we have to count the diagonals here.
I won't even try.
We will now determine the measures of the angles of regular polygons. We already know that equilateral triangles are equiangular, so each angle measures 60 degrees, and each angle of a square is a right angle. I will now distribute cutouts of 6 regular polygons to you, and I want you to measure their interior angles. Maurice, can you explain to the class what you wrote?
Well, when I used the protractor, the measure was somewhat midway between 128 degrees and 129 degrees. So I wrote that it's approximately 128.
Alright then. Now let's look at our table here. Can you find any pattern in the entries?
Well, the angles are increasing, but I can't see any pattern in the measures.
Why don't we expand our table by adding a column for the sum of the measures of the angles?
Why should we do that?
You'll see. What can you observe about the sums of the angle measures?
Except when n is equal to 7, each sum is a multiple of 180 degrees.
But when you round it off the whole number, the result is 900, which is also a multiple of 180 degrees.
As the number of the vertices increases by 1, the sum of the angles increases by 180 degrees.
Can you express the sum of the angles in terms of the number of vertices or sides?
Well, 180 equals 1 times 180. 360 is equal to 2 times 180. 540 is equal to 3 times 180. 720 is equal to 4 times 180. 900 is equal to 5 times 180, and so on. In each case, the multiplier is equal to the number of sides or vertices decreased by 2.
So, if we let n be the number of vertices and s represents the sum of the angle measures, then we have s is equal to n minus 2 multiplied by 180.
Yes, that's right. So what is the formula for the measure of each angle?
That's easy. Since the angles are all congruent, we just divide s by the number of angles or vertices.
Alright then. If we let theta denote the measure of each angle, then we have the following formulas. S is equal to n minus 2 times 180 degrees. Theta is equal to s over n is equal to n minus 2 times 180 degrees all over n.
Miss Cristel, why is the sum of the angles a multiple of 180 degrees?
That's a good question. From our past lessons, what does 180 degrees remind you of?
It's the sum of the measures of any triangle.
Yes, that's right. So this suggests that we break up a polygon into triangles. We do this by drawing the diagonals through a given vertex. Can you see a pattern in the number of triangles formed?
The number of triangles increased by 1 as the number of the sides increases by 1. And the number of the triangles is 2 less than the number of the sides.
Very good, Jay. So if you have a polygon with n sides, into how many triangles can we subdivide it with our method?
There will be n minus 2 triangles, so that's the connection with the table we got.
Take a look at this figure. Note that all the interior angles of the triangles make up the interior angles of the polygon.
Which means that the sum of the measures of the interior angles of the triangles is equal to the sum of the measures of the interior angles of the polygon.
Since there are n minus 2 triangles, the total measure of the angles is n minus 2 times 180 degrees, and each angle of the polygon measures n minus 2 multiplied by 180 over n degrees.
Yes, that is right. So we have now proven that the formulas we obtained earlier are correct.
Miss, will the sum of the angles still be the same even if the polygon is not regular?
That's a good question. Well, class, what do you think?
I think it would still be the same, since we would still have the same number of triangles. And the sum of the measures of the angles in each triangle will still be 180 degrees.
Yes, that is correct. However, we can no longer use our formula for measure of each interior angle, since this time they are no longer all congruent. We have one more thing to investigate. This time, we will find a formula for the area of a regular polygon. Can you recall the formula for the area of a triangle?
It's equal to 1/2 the product of the base and the height.
That's correct. We will use it to find the area of a regular polygon.
How do we do that?
We will again subdivide the polygon into several triangles. This time, however, we will not draw diagonals from a given vertex. Instead, we will connect the vertices with the center.
Where would that be, Miss Cristel?
Just like in the circle, it's the point interior to the polygon that is equidistant from the vertices. If we join the center to each of the vertices, we form as many triangles as the number of vertices. Now, look at the triangles that we formed. How are these triangles related?
They look congruent to me.
Can you prove that they are?
Well, the sides which are also the sides of the polygon are congruent, since the polygon is regular.
The sides joining the center to each vertex are also congruent, since the center is equidistant from all the vertices.
Then all the triangles are congruent to each other by the SSS postulate.
Which means they all have the same area.
How does that enable us to determine the area of the polygon?
We just get the area of one triangle and multiply by the number of triangles.
Can you give an explicit formula for the area of a regular polygon? Let n represent the number of sides or vertices.
If we let h be the height of one triangle and s the length of each side of the polygon, then the area A would be n times the area of one triangle, or A equals n times 1/2 sh.
Very good, Tisa.
Miss Cristel, is there a way we can get the value of h when the length s of each side is given?
In general, you will have to have some knowledge of trigonometry, which is the study of triangle measurements and other related properties, to be able to compute h when only n and s are given. But in the case of a hexagon, Yes, we can get the value of h.
Why is the hexagon special?
Do you recall the measure of an interior angle of a hexagon?
From the table we had earlier and also by using our formula, it would be theta is equal to n minus 2 times 180 degrees over n is equal to 4 times 180 over 6 and equal to 720 over 6, which is equal to 120 degrees.
That's right. So the base angles of each triangle would each measure 60 degrees.
That makes the third angle 60 degrees as well, doesn't it?
Yes, that's right. So each triangle is equilateral. Now, if we draw the altitude from the center, the triangle divides into two 30, 60, 90 triangles. Can you give me the value of h?
If I remember correctly, in a 30, 60, 90 triangle, the side opposite the 60-degree angle is square root of 3 over 2 times the length of the hypotenuse.
So if we apply our formula for the area to a hexagon, we get A is equal to 6 times 1/2 times S times square root of 3 over 2S, which is equal to 3/2 times square root of 3S squared. Let's now summarize the formulas we learned today. Maurice, can you start with the diagonals?
The number of diagonals that pass through a given vertex in a polygon with n sides is equal to n minus 3. And the total number of diagonals is 1/2 times n minus 3.
For the angles, the sum of the measures of the interior angles of a polygon with n sides is n minus 2 times 180. If the polygon is regular, then the measure of each interior angle is n minus 2 times 180 degrees all over n.
We also show that the area of a regular polygon can be computed using the formula A equals n times 1/2 SH, where n is the number of sides, S is the length of each side, and H is the height of each triangle formed by joining the center to the vertices of a polygon.
Not to forget, we also learned how the polygons got their names.
All these formulas are making me hungry now.
Then perhaps I should start calling you a decavore.
Why? What does that mean?
An animal that eats 10 times a day. What else?
Yeah!